Alright, it's good to see everyone again today. So today is going to be a short video on using the Lagrangian multiplier method to solve constrained optimization problems. So say that you have a utility function that looks like this. Utility is a function of goods X and good Y. And let's say that this individual, let's call her Nancy. Nancy has preferences which can be represented by the functional form of her utility is determined by the product of x to the 1/6 times x to the 5/6. And the price of x is equal to, let's call it 1, and the price of y is equal to, let's call it 3. And that Nancy's total budget is equal to, what's something easy? Let's call it 30. Okay. So the constrained optimization problem would be set up as follows. You're trying to maximize, you're trying to pick X and Y, a consumption bundle that maximizes her utility, Nancy's utility, which is given by X to the 1/6 times Y to the 5/6, subject to the constraint that the total amount of money that she spends on these goods, sorry, let me erase that, which is going to be equal to 1, which is the price of X, times X, plus 3, which is the price of Y, times Y, must be less than or equal to 30. Right, so this is the constrained optimization problem. Well, luckily for us, there's a few tricks that we can use to simplify this problem and solve it. Let's see here. Okay, so first step is we're going to use the method known as the Lagrangian multiplier method. So I'm just going to go over it heuristically without explaining the nuances of the method in this video, and we'll go over those in class or in a subsequent video. So basically what you're doing, you're going to set up what's called a Lagrangian function, and it's going to look like this. The Lagrangian function is going to be equal to the utility function minus the budget constraint multiplied by lambda, which is what we call the Lagrangian multiplier. So the budget constraint will take a form that looks like this: pxx plus pyy minus m. Notice that pxx plus pyy minus m must equal 0, right? That when pxx plus py minus m equals 0, that means that the budget constraint is being satisfied. So essentially what the Lagrangian multiplier is doing is you're taking the utility function and you're subtracting lambda times 0, right? Which is just equal to u. So you're not breaking any rules of algebra. You're just adding 0 to a function, which you can always do without changing the value of the function, because adding 0 to anything leads to whatever it is you added 0 to. But this serves a very useful role. It's not useless. Okay, so now let's do the actual problem. Let me see if I can move this video down here a little bit. Maybe not. Okay, that's fine. Goodbye, video. Actually, we'll leave the video there. Okay, so in this case, we're going to try and maximize. We're going to pick x, y, and lambda that maximizes the Lagrangian function, which in this case is going to be equal to x to the 1/6 times y to the 5/6 minus lambda times the budget constraint all put on one side. So px is equal to 1, so you're going to get x plus 3y minus 30. Once again, notice that this is going to equal to 0 for any combination of x and y which lies on the budget constraint. Because that's just the definition of budget constraint. Okay, so now that we set up our unconstrained maximization problem using the Lagrangian multiplier method, We can solve it by just taking the three first order conditions and solving those for x, y, and lambda, which you don't actually need lambda, but it's part of the process. So this is now an unconstrained optimization problem. Okay, now the video is going away. So you have three first order conditions. The first order condition is the partial derivative of of the Lagrangian with respect to x. The second first order condition is the partial derivative of the Lagrangian with respect to y. And the third first order condition is the partial derivative of the Lagrangian with respect to lambda. All right? Because we have these three variables which we are maximizing with respect to. And you set each of these first order conditions equal to 0. And when you set all these equal to 0, then you have found the combinations of x, y, and lambda, which will maximize the utility function subject to the budget constraint. So now let's work through some math. So the partial derivative of f with respect to x, using the power rule, is going to be you bring down 1/6 times x to the negative 5/6, because you're subtracting 1 from 1/6, times y to the 5/6 minus lambda. Because notice that here we have x right here. We have lambda, so negative lambda times 1 times x, which yields just negative 1. And of course, we set that equal to 0. And simplifying that a bit, simplifying that a bit, it's just going to be equal to y times 5 to the 6 all over 6x to the 5/6 equal to lambda. Because all we did was take the negative lambda and added lambda to both sides. Right? So this expression represents our first order condition. So any combination of y and x that satisfy this condition satisfies our first order condition. So the second first order condition is the partial of the Lagrangian with respect to y, and you get, using the power rule, you get 5/6 times x to the 1/6 all over 5 to the 1/6. Sorry, I don't know why I said 5. I meant to say y. Okay. Minus lambda 3 is equal to 0. And notice that when we simplify, we can just add lambda 3 to both sides, and you get this. And the third first order condition is just going to be, we're just taking the partial derivative of the Lagrangian with respect to lambda, and you're just going to get the budget constraint. We're just rederiving the budget constraint. We're just separating out the budget constraint from the Lagrangian. So you get something that looks like this. I'm just going to rewrite it so that it's a little bit cleaner. Because notice, so a really common mistake that students make is that they forget that there's a negative sign in front of lambda. So the negative gets distributed throughout the parentheses when you take the first derivative with respect to lambda. So you get 30 minus x minus 3y is equal to 0. So that's the third first order condition. So now all we have to do is find the combination of x and y, which solves all three, which satisfies all three of these equations. Well, one very simple and very useful algebra trick is that we can take the first order condition and divide it by the second order condition, which allows us to simplify a lot of this algebra. So we can divide the right side and the left side. Right? And you're always allowed to do that because as long as you do the same thing to both sides, you're not breaking any basic rules of algebra. So now we're going to take this. We're going to take this pretty big, kind of confusing expression and simplify it. And the beauty of this trick is that everything simplifies down really nicely. So first, notice that, well, first let's take this big, ugly-looking fraction and multiply by the reciprocal, which is the same thing as dividing fractions. So you get y times 5 to the 6th times 6y to the 1/6 divided by 6x to the 5/6 times 5x to the 1/6, which must equal 1/3. And continuing the simplification process down here, when you're multiplying the same variable but with different exponents, you can just add the exponents and combine the variable. So this top portion just becomes y, because 5/6 plus 1/6 equals 1. So this top portion becomes 6y divided by 6 times 5, so just 6 times 5 times x. And I'm obviously going to cancel out the 6's in about 1 second. Go. Cancel out the 6's. And that must be equal to 1/3. So now we have this very, very convenient, very simple expression that y over x, y over 5x, must equal 1/3, which is, or stated another way, y must be equal to 5/3 x. Any combination of y and x that satisfy this simple equation must also simultaneously satisfy the two first-order conditions, these, right? So that's the connection between this equation, this combination of y and x, and the two first-order conditions. So now what we can do is just plug in this equation into the third first-order condition, which ensures that whatever combination of y and x we do pick, which will automatically satisfy the first two first-order conditions, will also satisfy the budget constraint. So now we have 30, sorry, let me switch back to white. 30 minus, well, let's do 30 is going to be equal to, I'm just moving the x and the 3y to the other side by adding both sides. 30 is equal to x plus 3, and then plug this in, times 5/3 x. And very, very conveniently, the 3's cancel, and you get that 30 must be equal to 6x, which implies that x is equal to 30 divided by 6, which is equal to 5. What a nice, convenient, clean solution. And of course, we're not done yet, because now we have to find the optimal y. And just plugging this y, the optimal value for x must be equal to 5. We can just plug that into this equation right here. We get that y star, the optimal y, must be equal to 5/3 times 5, which is equal to 25 divided by 3. And we are done. We have found the best feasible bundle. And we know this is the first feasible bundle because this combination of x and y satisfies both of the first two first-order conditions, which we know it satisfies because both of those satisfy this equation down here, that y is equal to 5/3 x. And we also know that it satisfies the third first-order condition, the budget constraint, because we just plugged it into the budget constraint. Thus, we have found a combination of x and y which satisfies all three first-order conditions, which means it is maximizing the value of our Lagrangian multiplier, which is another way of saying it is maximizing our constraint optimization problem, which is the utility function subject to the budget constraint. So there you have it. A not so simple, kind of convoluted, but relatively easy way of solving a constrained optimization problem.